Hello again and welcome back to part 3 where we're looking at Industry 4.0, the robotic teleoperation process and its impact on the future Internet of Skills. My name is Alfie Keary. I work for the Tyndall National Institute and also working with our other two partners, Analog Devices and Imdala Technologies. What we're going to do here is provide an extract of a number of videos that were compiled in relation to specific research we're doing on robotic teleoperation. You know already now the role that it's going to play in the advancements of the Internet of Skills. So I will briefly talk over a number of videos. They are basically 5 videos. Part 1 will look at a proof of concept. Part 2 we'll look at the edge components of teleoperations. We'll talk about time-of-flight technology in part 3. Then we'll go into look at the embedded AI research work that is going on with in the project led by our partner Imdala Technologies. And then we'll just discuss the overall bringing the whole platform together and the issues that we've already talked about, latency as well, in terms of the real potential for robotic teleoperation. So we'll let the videos play and I will just briefly mention any points that are relevant as we work through. The first video is a proof of concept where we built everything, but in the lab context. This is the labs at Tyndall. So I'll talk about the first video. In this video here, you can see that one of our colleagues, Owen is wired up with various sensors. You can see that this is a glove which gives you full freedom to actually manipulate the fingers, and it moves the arm of the robot. And also there's a tracker which is specifically in this proof of concept used to actually move the actual robot, the arm of the robot itself. So the glove is moving the fingers and the actual tracker is used to move the arm. So this is proof of concept work that went on, and you could think of Owen being located in let's say Dublin, Ireland, and the robot being located in Paris, France, for example. So this is a setup in the lab, but clearly the whole concept of a remote end and a local end. In this particular example, we would say that Owen is at the local end, the user end, and the robot is located at the remote end of the teleoperation platform. So we'll just finish out that video there, and you can see so the precise movement, etc., and everything that was required to actually manipulate the blocks. So what you're seeing there is basically sensory fusion at the local end, and then that data is transmitted across a communication platform to a robot which will carry out a predefined task. Digital twins, basically it's very early stage work, and what we found here is that this is a representation of our robot. We're representing the block world, as you saw in the previous video. We're actually specifying how the blocks could be moved in a virtual space. This turned out to be an extremely complex problem. So the potential for digital twins, we believe, is paramount for robotic teleoperation in the future, and all the potential when you merge digital twins with virtual reality and augmented reality. But it is today the technology to really develop true digital twins such that a user could walk into something similar to the metaverse at a local end and have a process and a task completed by a suite of robots at a remote end. That's where we're going with Internet of Skills, but clearly there is a lot of stages and a lot of research and a lot of advancements in terms of virtual worlds or the metaverse, which is the term that has been coined recently, to enable true digital twin technology in the future. Looking at the next video, we're just going to briefly explain this is the specific edge-to-edge infrastructure that has been built as part of the project, and I'll talk about it briefly on the next video. This is really just the software setup. It's just demonstrating that to you. But you can see here that this is a typical setup. These are the edge processors. We're zooming in there. You can see the specific edge processors that are making up the actual project. So very, very briefly, this is a Rapid ID technology down here. This is the STM32s. There's also a Polar Fire in the video, which will be integrated into the platform. This is the industrial Ethernet protocol called Profinet. This is a PLC device. So again, this is obviously established at the labs of the project partners, but you can think about one of these edge devices representing the local end and the second edge device representing the remote end of a platform. Now, typically in an industrial campus, which could maybe, let's say, a few kilometers, this could all be, there could be a remote end and a local end within a campus of that size, and that would use typically the industrial protocol infrastructure, the Profinet, which we are using in our project. But then you can expand that into a global scale across Europe or on a continental scale from one continent to another, where you have the connectivity between local and remote end. And thus, again, that's the type of the complexity of the problems that we're trying to deal with when we're doing research into latency and how AI innovations may be used to address latency and potentially predict ahead of time what a user wants to do in a set of reasonably predefined tasks. So I'll just play out the video. So you can see this edge infrastructure, and then of course that's connected to the robot, which is carrying out again, we just work and we test this on the typical block world to see that the robot arm and the gripper is actually working. So that gives you an idea. So far we've looked at the first proof of concept, we've talked about digital twins, and then we've looked at really the local edge to the remote edge of the robotic teleoperations research work we're doing in the IMOCO. Now, this takes you on a journey to the Catalyst lab from analog devices. So a colleague of ours, Nihal, works for analog devices, and her real focus is using the vision time of flight technology to drive a robot. Here you can see where the work is at the moment, where we're moving a wrist in the three-dimensional space, and a lot of the work is addressing the latency between the sensor and driving the robot in real time. I'll leave you have a look at the video. So you can see that is actually pretty impressive performance, but that took considerable research. So what we're seeing here at the moment is that the time of flight technology is being implemented on a PC and also on a device called a Nuke, which ADI work with in terms of it's similar to an edge processor, but the optimization and the latency that ADI and the other partners on this project were working on to get that smoothness of the robot to be able to move in real time. So think about it, the time of flight technology is processing the image, all of the AI processing has to go on, and that has to be then communicated across a communication network and drive the robot in real time. So considerable work goes on in what seems relatively easy, but major research behind that. An idea of the typical sensor work. So we're replacing the actual motion trackers with the real time of flight vision tracking. Now we're saying we know that teleoperation is inherently problematic because of latency. So we're doing work in terms of how with the embedded AI we can start to have more innovative capabilities to assist a user in robotic teleoperation. So one of the aspects is gesture recognition is ideal because with more advanced gesture capabilities in the future, predefined gestures can position a robot to do a particular task or get into a specific standing format or configuration of its various end effectors. So gesture recognition is one aspect, and then we're trying to look at the real, how can we predict ahead of time where the user's hand is going to be or fingers in the future, but primarily at the moment we're focused on where the actual arm is going to move to, and we're using the focal point of the joint to actually identify that. I'll play the videos and just talk briefly. So there are, this is around for quite a number of years, and gesture recognition has got quite advanced. We're using gesture recognition with time of flight technology. So clearly here, we're just showing some tests on one of our researchers putting up their fingers to indicate different numbers which are identified by the gesture recognition algorithms. Now, in the future, you could look at very customized gestures which could be set up, and you can engineer the embedded AI to recognize those customized gestures, and that may do very specific tasks which could save a lot of time in robotic teleoperation. And that of course means then that there's less data to be communicated when you want to get the robot to do a certain task, and that indirectly is reducing latency in terms of the activities for remote teleoperation. I'll just finish out this video there. And finally here, we're going to have a look at what we're using is looking at using embedded AI to actually predict ahead of time, because the actual time of flight technology will actually lose track of the wrist from time to time. So what we're looking at is using mathematical and related AI algorithms that can actually, when there's a drop in the tracking of the wrist, that the algorithm kicks in and identifies where the wrist is most likely to be. So we'll show you an example of poor tracking. The green is where the wrist is, and the gray is the computation of the poor tracking in this case, and also you see an example of good tracking in the second video. So I'll just play the video there. So you can see here that it's quite poor in terms of trying to identify where the wrist is. You can see that this is quite accurate in terms of finding the wrist in most occasions when there are frames dropped with the time of flight sensor technology. So that's always going to be the potential. We're always going to have noise and interference, and sensors will not always be guaranteed to be 100%. Even if they're 99.9999%, there will be a fraction of error and failure in sensor computing capabilities. So that's where the research in AI and embedded AI research is ongoing. And particularly our focus is try to have algorithms that will have knowledge of the task to be computed and be able to predict ahead of time when a certain task needs to be carried out at a remote end in a robotic teleoperation. The final video, and here this is, I suppose, bringing it all together with the time of flight and the AI algorithms, and I'll just leave this video play out. As you can see, this is work that took place at the Catalyst Center in terms of driving the robot in real time with the Kalman filter. We use a Kalman filter here at the moment to actually intervene when there's a frame drop on the actual time of flight camera technology. And you'll see the robot moves quite smoothly in this demonstration with my two colleagues, that's Nihal Amer and Alan Dunn. So again, to remind you, what's happening here is the tracking is going on in real time, and obviously there's an overhead here because you have the graphical representation of what's happening on the monitor you're looking at there. So that's introducing latency into this platform, so that will have an impact on the real-time speed of the robot. But it's just to visualize it, and what you're seeing here is that as Alan is moving his wrist, and when the technology fails, the sensors fail, the AI kicks in and it does a step ahead projection of where the wrist should be. But you can see that the robot moves quite smoothly in terms of this testing setup at the Catalyst Center. So I'll just leave that video finish out. And you can see there, obviously there's flashing between the different colors, and when you see the color change, the green is indicating the actual correct time of flight identification of the wrist, and when the color changes, it's where the embedded algorithms are kicking in and making a prediction. So you can see it's really a edge embedded AI prediction work that's core to the type of research that is being conducted by the three partners involved in the robotic teleoperations platform. So look, that's it. That's more the practical side of the work we're doing in the Emoco project. So I will talk to you again when we have a wrap up of our module and just revise a number of points we discussed already in relation to the Internet of Skills. So I'll talk to you soon, and thank you very much for watching.